Today I'm going to talk about the coupling functions, in particular neural cross-frequency coupling functions, and I'm going to look at this delta alpha interaction in three applications: in resting state, in anesthesia, and in sleep. So my talk is going to be along experimental lines of reconstruction of networks data and application to neuroscience. So the objective of my talk will be how to reconstruct coupling functions from data. And I'm going to talk about, as I mentioned, three applications. First, I'm going to start by laying out some basics about coupling functions. Then I'm going to talk about methods of how to reconstruct the coupling functions, what we should use, what one can do there, and so on. And then I'm going to move to the three application, as I mentioned, brain resting state with two states with the eyes open and eyes closed. Then we're going to have a general anesthesia where we're going to look at two types of anesthetics, propofol and sevoflurane. And in the end, I'm going to talk about sleep and a natural state of sleep. So recently, or not so recently, even now, there was increased interest in coupling functions, and that was going on in theory. Different types of coupling functions, different types of treatment of coupling function, how they can lead to some phenomena like synchronization, clustering, and so on. Then powerful methods were developed recently and not so recently about dynamical inference, where one can reconstruct these coupling functions from data. And then these methods led to various different applications, like in chemistry, physiology, secure encryption, climate change, economics, society, science, and so on, and a lot of works in neuroscience, probably. Most of the works were connected in some way with neuroscience. Yeah, arguably the biggest interest was in neuroscience. If you look at the papers that were published recently on coupling functions, in some way, most of them are in neuroscience. Why is this so? Because of the fact that the brain is heavily connected. We have a lot of connections on very different levels, and these connections, this connectivity plays a very crucial role in different functions that the brain can mediate. So knowing these mechanisms behind this connectivity, which can be explained partially by coupling function, is very important. Recently, we had a review on the topic, so yeah, this is maybe why we are linked with Tiago and Neta and Peter. And we recently had also a team issue in philosophical transaction A on coupling function, which included both papers about theory, methods, and application. This is the list of authors. There was Kuramoto, Freestone, Marcadi, Misha were there, Istvan Kish, Ermentrout, and so on. So some basics about coupling functions. So we are looking at couple oscillators. So they can be more general phase and amplitude and so on. In this talk, I'm going to stay on phase dynamics. We're going to look at the couple dynamical systems. If they're oscillator, one can apply the phase reduction procedures where we approximate the high dimension dynamics of an oscillator by a one-dimensional phase. There were many talks, Marcadi and the others, which give more details about this and the equations and so on. So I just mentioned it briefly. So we end up with a differential equation for the phase. We have a frequency parameter, and then we have the coupling function depending in this here in this example pairwise on two phases, and maybe we have some noise, so we have a stochastic differential equation, or if we don't have the noise, we have ordinary. For example, the coupling function can be a sign of the phase difference. We have some coupling parameter which gives the strength of the function, and so on. So in this way, we say that we are interested with the coupling function to describe how the interaction occurs and manifests. So we are not interested only in if there is interaction and how strong is the interaction, but also here we stress that with a coupling function we can find the mechanism, the functional law, which describes how the interaction is going on. If we know how, if we know the mechanism, we can try to find qualitative transitions like synchronization or clustering and so on. And the main additional information that a coupling function brings is the form of the function, right? So we get more insight into the interactions if we are looking at this form of the function. More examples, not to be too abstract, so we can have the famous Wim-free coupling function or the Kuramoto coupling function, which he used in his model. So Wim-free coupling function has a product form of two functions. One is the perturbation function depending on the other system, and the other one is how the system is responding, or the phase response curve. They can be, for example, sine and cosine, or the Kuramoto sine function of the phase difference, which looks very familiar. Another simple example. So this is the simplest it can get, so we can try to see what the coupling function can tell us, or how we can connect what we see in the data. So my talk and everything that I will speak will be about the data. So let's see what the coupling function can tell us from the data that we measure. So I'm going to consider the simplest case. We have two phase oscillator. One is autonomous, driving the second one. We have frequency and some coupling functions, which is in the simplest form, let's say cosine of E1 plus maybe some shift. So the first one is driving the second one. We have a time series cycle of the first one, and we have time series of the second one. This will be the usual one that we measure in experiments. So if we have a phase coupling function in the full two-dimensional space, or because it depends on only one phase here, we can average and just have it like this. And then what we can see is that when the coupling function is increasing, we have the oscillation of the second one being accelerated, and then when the coupling function is decreasing, we have the oscillation of the second one decelerating. So in this way, we can learn when the oscillation of the second one are accelerating or decelerating as an effect of the first oscillator as defined by the coupling function. Yeah, further more examples. So why study? Because they can reveal mechanism. I mentioned how is important. There was this nice paper in PRL 2006, so already a long time ago, where they looked this chemical, electrochemical oscillation, Belousov-Zhabotinsky. They were able to experimentally reconstruct the coupling function, out of which they were able to learn more details about when and how synchronization of these electrochemical oscillators will happen. Yeah. If you know the mechanism, of course, going back to the data, there are important implications for entropy methods and causality, like Granger causality and transfer entropy. Then we can use this coupling function to predict when synchronization or some other critical transition can happen. For example, Istvan Kiss had a paper where he observed 64 globally coupled electrochemical oscillators. He first reconstructed the coupling function, and then once he learned the details about the coupling function, he was able to predict if his system is going to be one or two cluster synchronized. So depending on the conditions and the coupling function, then he was able to tune them either in one cluster or in two clusters. This is 2 pi, and then we have two cluster states. So in this way, if you know how to predict using the coupling functions, they can be maybe used to maybe have early warnings about some critical transitions and so on. And now Istvan is talking about synchronization engineering. So right, if we know the coupling function, we can engineer the behavior, which is the outcome of the interaction. We can decompose the net coupling function into components like direct, if it depends only on one phase, or both. You call this indirect, or actually it's better to call it common, like depending on the two. And we can do this also, I will mention, for non-pairwise, where we call them direct from 2, common from 3, and so on. So we can describe these subcoupling components in the net coupling function that we are observing. I'll show another example, why coupling functions are important. Something that I was inspired to look, because the data that we are dealing with are from biological systems, so often they are time varying. So in many cases, we are seeing that what the net coupling strength often doesn't change, doesn't vary in time as the coupling function is varying. So sometimes these are bringing two different information. So I try to build up a case, extreme example, where I'm going to try to make the form of the coupling function to vary with time, but the coupling strength to be constant all the time. Just to illustrate this, I'll use an extreme example to show this. So what I'm doing, this is my model. I have unidirectionally coupled systems. Again, simple, I want to keep it simple. The second one is driving the first one. We have frequency, and we have the net coupling function with some coupling strength, net coupling strength, which is the whole direction from the second to the first, and can be time varying. And I set this to be the one sine and one cosine of the phase difference, and I have two subcoupling components, C1 and C2, which are changing in time reversely from how I will get the net coupling strength, doing the Euclidean norm. So I'm doing like increasing one and decreasing the other, so that the square root of sum of their squares is always 1. And then I'm trying to see if having constant net coupling strength all the time, but varying form of the function can bring synchronization transition. We had, there was this paper that I wrote, and then with Hagos and Tiago, we also wrote another paper similar to this, and this is the result. So we have time, all the time the same time. So I'm varying the red and the blue subcoupling components in such a way that in each point of time, if I take the Euclidean norm for the coupling strength, it's constant. While if you're looking at the coupling function, comparing in time, this is the arrows where they were plotted in time, we can see that there is it slowly varying in time. So for example, if you compare the first one and the last one, they are quite shifted, the wave is shifted, right? So the form is changing, the coupling strength is not changing, and in this case, the frequency was such that it was close to synchronization, and at some point we can have transition from not synchronization to transition state, so to synchronization state. So we can have a critical transition because of the form change in time. And this has a big implication also for causality measures and fold-off measures, which are trying to find the net coupling strength or the strength of the information flow in one direction. So if you try to reconstruct a network with nodes and edge, so even if you know that there is edge, this is not the whole picture, what I try to say. That there are more information that can be hidden in the form of the function, which can act as another dimension, and there can be changes like qualitative transitions only due to this. I usually have very small slide mentioning this, but at this conference everybody was speaking about non-pairwise and hypergraphs and high-order networks and so on. So I want to advertise a bit more, so I put one more slide for this paper. 2015, we had a paper following some other words like Bjorn paper, and then, okay, now there is a review. Maxim is there, or what Eddie was talking, and so on. So I just want to stress that 2015, we had a paper where we did use triplets and quadruplets, and we applied to neural data, but we were calling them multivariate coupling functions, right? So different name, but the same thing. And we look at these neural cross-frequency coupling functions where we had the 5 brain waves. I'm going to talk about this in the application later on. Here we tried to infer the 5 oscillators, including triplets and quadruplets, and try to see how they look and are they significant to surrogates and so on. So first we had a small example with 5 phase oscillators. We had surrogates. We had including triplets and quadruplets, and we were changing with time. And then we applied to the brain where we have EEG. We decompose the 5. We filter out the 5 brain waves, and then we try to find the different couplings. This is a coupling strand. This is the pairwise delta alpha, but this one is the triplet theta alpha and gamma into gamma. Similarly, we also reconstruct a coupling function. This is the theta alpha into gamma. This is more like direct from 2 into gamma, because this is the most we can visualize, but we also calculated quadruplets and so on, which we cannot show. Okay, so that was shortly about coupling functions. Briefly, I'm going to mention about methods. So we need methods which can reconstruct this from data. So these are methods performing dynamical inference. Often they are called filtering or causal inference and so on. So it's the same thing. Practically, they want to reconstruct a model in terms of differential equations from analysis of time series. If we know the equations, we know the system in detail, and in this way we are inferring mechanisms. Or in neuroscience, they call this effective connectivity. So we have structural, functional. What we are doing with this, we are actually doing effective connectivity. We have some data. We need to do some pre-estimation, try to find the phase, amplitude, maybe proto-phase to phase, and then we have some kind of model. Today I'm going to talk about phase dynamics, so phase oscillators, and then we infer to find these coupling functions. There are a lot of methods starting from Kalman filter and so on, which were doing this dynamical inference. Many of them had coupling functions as an implicit internal part. Here we also try to look coupling function explicitly and to try to assess them and further analyze their properties. Some methods, I will just mention them: least square fitting, Arkady Misha, maybe one of the first in physics, reconstruction of coupling function, then maximum likelihood multiple shooting, random phase resetting method, dynamical modeling, bias factor, dynamical causal modeling, very popular in neuroscience, and I'm going to talk about dynamical Bayesian inference. So again, we have this phase oscillator. Because it's an oscillator, I can decompose the coupling function into Fourier series, starting from time series from noisy interacting systems. We assume such a model. We apply Bayesian inferential framework in order to infer the parameters, which can also be time varying. And after I have the parameters, I can talk about directionality, synchronization, or the all-important coupling functions. So 2 things I need to find. One is the time-varying parameters and the noise matrix D. We apply Bayesian probabilistic theory in such a way that we use multivariate Gaussian distribution for the prior, and the method will give me also Gaussian distribution for the posterior. We have white noise So again, another Gaussian. And after recursive evaluation, we get the posterior distribution given with a vector of mean values of the parameters and a covariance matrix which define explicitly mind dynamics. In this method, we design a special procedure for information propagation between windows so that the new prior doesn't become the whole posterior, but there is some sigma dispersion in order to allow the method to have certain freedom to follow the variability of the parameters, the variability of the dynamics, but also try to infer precisely the noise. And I jumped many details. You can check in these papers. Whenever we infer couplings from data, we need to have some kind of verification. So we usually use surrogates or surrogate data testing. This is a procedure when we generate independent, uncoupled signals with same statistical properties, and then we try the methods on them, and what we infer should be the non-coupled couplings, and then we do many realization of this and having some statistical interval like mean plus 2 standard deviation, we can define a threshold or a zero value above which we can say that what we infer is statistically significant. Once we have the coupling functions, we want to use them somehow, right? Often when working especially in this application, biological, we want somehow to get some properties. So coupling function analysis is something that, like, trying to use the knowledge of the coupling function or to try to quantify the form of the coupling function so that we can make some quantitative statistics. One very useful way is the similarity of coupling function, introduced by Bjorn et al., which tries to find the correlation and actually gives a number from -1 to 1 if two coupling functions are similar enough, irrespectively of their strength. So only quantifying the form of the function. We extended this into polar similarity, where we also have the angle, the phase where they are mostly similar. Like if we have a predefined function and we slide it along, we can find the angle where given with the arrow, and the length of the arrow is how similar they are. I'm going to use this later on for describing the data. So these are the methods, and I'm going to slowly move to the applications. The first application is about resting state with eyes open, eyes closed. In neuroscience, they have this subfield of cross-frequency coupling, where they try to find the couplings between brain waves, so delta, alpha, beta, theta, and gamma. We extend this now for coupling function and called it a neural cross-frequency coupling function analysis. Here I'm going to use phase-to-phase. They can be phase-to-amplitude, amplitude-to-amplitude, and so on. I'm going to concentrate on phase-to-phase. We have EEG from data, and then we try to infer the coupling function. I'm going to look at the eyes open, eyes closed, human resting state. We had 16 subjects, and I'm going to focus here only on delta to alpha coupling function. Actually, in all my talk, the title had delta to alpha. In the second one, I will show more interactions, but I wanted to stress the delta to alpha, so I'm focusing on this interaction in particular. As we always do, we first do wavelet power to see how the oscillations look. Are they there? What we are going to analyze. This is the wavelet time average, so it's frequency and power. We have the delta, theta, alpha, beta, gamma. The blue is for the eyes open, and the red is for the eyes closed. All the figures are with this color coding. This is the line, and then if we take the intervals and compare, we see that there are statistical differences in all of the intervals for each brainwave. So importantly for delta and alpha, there are significant differences. And then we try to analyze coupling strength. We try to find how many of them are significant to surrogates, and we have, this is for the eyes open and this is for the eyes closed. Comparing them, we can see that there are more interactions which are significant in the eyes closed state and much less when they are eyes open. The coupling function here was a very varying story. So sometimes you get them, sometimes you don't. Sometimes they are very varying, sometimes they are more stable, and so on. In general, they were better for eyes closed and not so for the eyes open case. Here is a good example, here is a bad example. So here we have the phase of the delta, phase of the alpha, and this is into the dynamics of alpha, right? Delta to alpha. These are the connections that we are observing, and this is an average of all the subjects. Here we have the polar similarity. The individual dots are for each subject, and then this is an average showing the angle where this is the most similar to a predefined function, and the length of the arrow is the similarity. There is some shift between the waves in eyes open and eyes closed, and sometimes they are just too varying. We analyze how they vary in time. So here are two examples how coupling function vary in time. Again, this is eyes closed, this is eyes open, and this is the similarity index. This is time, and then the arrows show in which point of time we are considering them. So for example, here when they are very low, we see that they are varying, not very similar. Here when the index is high, we see that they are similar, and if we go in time, they are not very varying. There are only very small variations between them. For the eyes open case, they were more variable. We did quantitative analysis. We got that for the coupling strength, the coupling is much stronger for the eyes closed than the eyes open. This is consistent with previous studies. Different people found it, but now we also had information about the coupling function, which showed that also the form of the function is more significant, has better similarity than in eyes closed than in eyes open. The next application is about general anesthesia. This was one part of a big study, Braccia, involving more measurements and more analysis. This is only the part focusing on the brain and heart and respiration dynamics, and particularly in the brain parts, and trying to find some coupling information related to the different anesthetics. So the main question there was, what are the mechanisms? It's still open question with general anesthesia, how to trace or detect and follow depth of anesthesia, and so on. And there were three pillars in this study, three main parts. We study anesthesia with two widely used anesthetics, propofol and sevoflurane. We look at this neural cross-frequency coupling function to try to find coupling mechanisms, and we analyze three different organs. We had the brain, the heart, and the lungs. Here I show also the intervals, the frequency intervals that we use to extract and filter the different oscillations. So in the brain, we have delta, theta, alpha, beta, and gamma, the cardiac, and then the respiratory. We try to look interactions between the organs and within the brain intervals. There were 25 awake and 29 anesthetized healthy subjects, age 18 to 60, about to go surgery. These 29 were anesthetized, 14 with propofol and 15 with sevoflurane. And there were, for each subject, there were 2 sets of measurements when he's awake, he or her or she is awake, and then either anesthetized with propofol or sevoflurane by random choice. And the measurements were 20 minutes long. Of course, we apply surrogates to test the data, and this is one of the most dominant result that we got about this delta alpha coupling function. Actually, chronologically, first we did this and then the resting state, because here we also look different interactions. So here we have results for one subject, individual, and here we have group results for all the subjects. We have awake state, propofol, and sevoflurane under anesthesia. And what we can see here is that when we are awake, the coupling function is varying, not so stable, not significant to surrogates, and so on. While when we go to propofol, we get this nice shape, which is even more pronounced when we go to sevoflurane. So, for example, if we observe here, we have the phase of delta, phase of alpha going into alpha. So there are small changes along alpha, but they are predominantly changing on delta, which means that when delta is increasing, alpha oscillations are, when this coupling function is increasing, the alpha oscillations are accelerating, and here we have deceleration in alpha due to the influence from the delta oscillation. We analyze actually many more. Here we analyze all the possible combinations, and then we test them to surrogates, and these are the ones which were mostly significant to surrogates. So we have delta alpha, theta gamma, alpha gamma, respiration to theta, heart cardiac to theta, and then cardiorespiratory, respiration to heart. This is for awake, propofol, sevoflurane, and then we have surrogates. I won't go into detail in all of them. This is the same one that I show. Theta gamma, again, we have some which is stronger, some not. Alpha gamma, it's diagonal, meaning there is a common coupling both from alpha and gamma. Respiration to theta, here is better, in the middle is not so much. Here we have some, and for the cardiorespiratory, this is a known which we also observed before in other studies, and it was more varying the form of the function, even though the strength was stronger, the form was more varying when we went to anesthesia. We did quantitative analysis, so this is the coupling strength for 5 of them. 1 was not significant. There were some significant differences. We also decomposed like the direct influence or the common influence, and we have awake, propofol, and sevoflurane. Not going too much into detail, I will stress that there were some differences in some of them, sometimes more pronounced in the components and sometimes just in the net coupling. And then we also tried to quantify this similarity index for the form of the coupling function. And here we have delta to alpha, respiration to theta, and cardiorespiratory, respiration to heart. And interesting result was that in the first and the third, we have significant differences between all of them, but while in the delta alpha cognitive, we have increased effect by anesthesia, while in the cardiorespiratory, we had decreased similarity of the form of the function. We also analyzed the noise, right, because it's stochastic inference, so we have also information about the noise. One reviewer asked on the review in the paper, so we had a picture also with the noise. So this is the noise strength in delta, this is theta, respiration, alpha, gamma, and the heart. Sometimes there is no changes, sometimes we see changes. Usually we see that the noise is less with anesthesia, things get more calmer, less fluctuations, and so on. While for theta, this was exception, we got more fluctuation, more noise with propofol and sevoflurane. So this was about anesthesia. And my last application is about natural sleep. So we all sleep. We know it's a naturally recurring state of the mind and the body. We need this to restore many functions like the immune, nervous, skeletal, muscular system in order to maintain memory, cognitive functions, and so on. What is known is that while we are asleep, there is changes to the brainwave oscillations. In particular, there are changes into delta and alpha oscillations, also to other, but there are big changes in delta and alpha, which was very good situation to apply our method and try to see what happens to the delta alpha coupling, and also to link it with anesthesia and resting state. So our focus was on delta alpha and the different sleep stages when you're asleep. There were 20 PSG recordings, these polysonographs, which included EEG at 200 Hertz sampled. They included 8 hours, at least 8-hour night sleep. There were, practically in all of them, there were at least 3 EEG channels, FP1, prefrontal 1, then CZ, central, and then O1, occipital on the back of the brain. So we have frontal, central, and back. Also try to analyze if there are any special directions between the couplings. The EEG data were scored according to AASM protocol, American Academy of Sleep Medicine, in order to have these 5 sleep stages. So there were awake, NREM1 on non-REM sleep stage, NREM2, NREM3, and REM rapid eye movement. So these 5, and we tried to see how the delta alpha coupling function and coupling strength change in each of these sleep stages. We did this with a student, Dragana Manasova. She's now at the Sorbonne and Paris Brain Institute. This is the wavelet power. So here's the recording, the whole night recording, 8 hours. And this is a wavelet time frequency analysis. So we can see very clearly, this is the time average. So we see delta, theta, alpha, beta, and gamma. And we can see the strong brain waves in alpha and delta. And we can see very clearly that there are very many transitions, and frequency are coming and going, reappearing. They are sometimes a bit higher in frequency, sometimes a bit lower, and so on. This is just for one subject, analyzing all the group subjects, the intervals. This is for delta. We see that this is for awake, and REM 1, 2, 3, and then the REM stage. We can see that there is a small decrease, and then we have increase going to the REM. Or for awake, the alpha is higher than the rest, which are dropping down to some level and then staying around the same. After that, we applied the coupling function analysis, and these are the neural cross-frequency delta alpha for the 5 sleep stages. This is for awake, NREM1, NREM2, NREM3, and REM. We can see that awake was very varying and low. NREM was starting to be, but on average for the group, it was, again, not very strong, though it had some defined form. Then NREM3 was again varying, and then NREM2, and NREM3 we already started to have this well-shaped form, which was very pronounced when we observed the REM sleep stage. Analyzing the coupling strengths, observing them compared to surrogates level, we noticed that there is like a gradual increase from awake. Then NREM1 and NREM2 were kind of similar, and then NREM3 was already above surrogates, and REM was the strongest. There were significant differences between them. This was for the O1 electrode, so on the back, this is a group table for all of them. So this is for the frontal, the central, and the occipital on the back. If they are significant to surrogates, the values are with the bold text. So we see that in general, except this for NREM3 and REM, they are significant. And then we went and tried to find the spatial, like taking delta from one electrode going to the alpha of the other electrode. So we have FP1 delta going into central alpha and so on. And here we saw that when we go front to back, like front to central and front to back, they are significant. When we go central to front, so in the other direction, they were not significant. Then going again center to back, so direction from front to back, again they were significant. And then when we go the other way around, they were not significant. And this was exception, it was significant. So in general, we saw that there is like a gradual increase where the direction spatially was dominantly from front to back and not the other way around. We also tried to see if the form of the function has any spatial differences, but in general, they were qualitatively similar in form, but the differences were more into the strength of this function and how they are significant to surrogates. So, in summary, I talked about coupling function, how one can characterize this interaction mechanism. One should notice that I'm not talking about biological mechanisms, but about the interaction mechanism and how one can link this to biological or neuronal mechanism and function. It's more tricky and requires involvement also from medical people, which we are always trying to link. Yeah, I talk about coupling function. I present some basics. I talk about methods and 3 applications, and I focus more on the parts that we were involved more, so dynamical Bayesian inference and the 3 applications that I show. Having these 3 applications, so I was talking about delta alpha coupling function, and they were not randomly chosen, right? So we have resting state, and then either anesthesia or sleep. So my hypothesis was, is there something similar between them in delta alpha? Like, is there a difference? Because we know that sleep is different from anesthesia, right? So my question was, is it also different for delta alpha, or is it the same? And the general conclusion, the general conclusion is that they are qualitatively similar, right? So we didn't saw, there were some shifts, like the wave was changing, but the way the mechanism presented itself was very similar, and then sleep and anesthesia had some similarities between. So the integral conclusion from all of this is that from delta alpha there are some implications for using this as a measure for depth and loss of consciousness, but this of course requires more investigation and further verification from neurologists. With this, I'm giving the end of the end, so thank you for the attention. Of course, I'll mention that a lot of the work was done with Aneta and Peter in Lancaster and many collaborators from Lancaster, and of course with my students in Skopje, with my collaborators and so on. There's a tutorial and toolbox for the method if somebody is interested, and there is, of course, the review for more details about coupling functions. Thank you for your attention.